Indeed, as was already introduced, I will, I give this a sort of nice title, Optical Computers Light Up the Horizon, which has a few elements in there. Of course, we're going to look about what are computers, where can optics, photonics bring in a next step. And of course, the word horizon there. I mean, this is really looking towards the future. I will highlight a little bit, okay, what are the issues with computers as we know them. Then I will focus a little bit on photonic integration. What is that? What are optical chips? What are we talking about here? And finally, I will give a little bit of an overview where actually optics and photonics are nowadays starting to make an impact for the better, of course, in computing. So with this nice view of our campus, we now go to the first slide here to say, okay, when we talk about computers, I think, of course, it's a weird talk, right? I don't see my audience, but I'm guessing my audience is very mixed. And not everyone has a very advanced technical degree. So when we talk about computers, most people think this is a computer. And obviously, that's true. But this laptop here, as we see it, it hides a lot of things that are happening inside in the laptop. A computer is supposed to compute. And computing is actually relatively simple. There are a few elements there that are of importance. So a computer has, of course, compute elements, things that can do calculations. There will always be a communication element. I mean, you can think about communication, of course, between the elements that do computing, because there should be many, but also, and we can already see that in our computer if we open it, between different chips, the processor and the memory, for example, but also all the other cables that go to the one that goes to your screen, etc. And there's a storage part. Storage, also known as memory, that is to either for long-term or temporarily store stuff. So when we talk about computers, yes, there is a compute part, but the communicate part, so transporting information, and the storage part are equally important. They are just three sides of the same coin. I know I abuse that expression, but you understand what I mean here. If we look a little bit more into technical detail, okay, a laptop, it has a screen, it has all these peripherals, how we can interact, but the actual computing is typically taking place in something that we call a processor. In here, I show you on the left-hand side a picture of a processor. In this case, a relatively old processor. And it looks like this little package, typically a few by a few centimeters, a little bit flat. And it has all these pins at the bottom, wires that you can connect it to a motherboard, right? All these little electrical contacts. But what if we would open this up, what we would find inside is a chip or an integrated circuit. Nowadays, an electronic integrated circuit. And these electronic integrated circuits, at the moment, they hold billions of transistors. And whereas this electrical integrated circuit, it has a size on the order of, let's say, 2 by 2 centimeters, the transistor itself is becoming increasingly small. We are now looking at transistors that are in the nanometer scale. A nanometer is a billionth of a meter. So far, if we always see, things that are small and we compare it to the size, to the cross section of a hair, this is at least 1,000 times more smaller. So these transistors are inside, and transistors are the building block of, let's say, your classical electronic computers. It is a little bit more of a technical picture. Transistors are made in silicon, and transistors are basically devices with 3 ports. A source and a drain, so that's basically where a current is flowing, and a control port, what we call a gate. And the gate basically controls how much current can flow there. So the gate basically controls the electrical signal that goes through. In that sense, it's sort of a valve. And by an electrical signal on the gate, we can control the signal going through, the stream of current, the stream of electrons, for example. So these are the building blocks of our computers. And the success of our computers is based on the concept that we use a binary system. So a computer works with ones and zeros, as we often say. Huh? So where normally we count in 0, 1, 2, 3, 4, in a computer we count 0, 0, 0, 1, 1, 0, 1, 1, etc. That sounds nice, but that is also that's just, let's say, it's still an ASCII representation, a textual representation of what is actually happening. And what is actually happening is actually quite diverse. And it doesn't matter what's happening as long as we have something that has two states. And that state could be, let's say, high versus low. That could be yes versus no. That could be on versus off. Even right versus left. It doesn't really matter. As long as there are two states, we have a binary system. And with such a binary system, we can do operations. And in a computer, as we know them, again, we have these transistors. And as I was saying, transistors control a little bit the flow of the electrical signal. So we can think about using this transistor to actually manipulate the electrical signal and maybe do some operations or calculations, if you wish. So the pictures here show, okay, what if I want to do an operation, a so-called AND operation, A and B? So A and B, that means that, okay, if both A and B are a 1, I will get a 1 out. And if A and B are either of them is, or both of them are 0, I will get nothing out. And you can see how these transistors, basically little valves, if you put them cascaded in series with each other, and if you would imagine that we would have a flow of an electrical signal from the top all the way to the bottom, passing through two valves, you can easily imagine that only if the two valves are open, so only if there's a 1 on A and a 1 on B, then I would actually have a flow. So then I would have a 1 at the output. If both of these valves or one of these is a 0, it won't happen, right? I can also make an OR operation. That means signal can flow from top to bottom through this valve or through the other valve. But if one would be closed, the signal would still flow. So this is just to give you a little bit of a taste of what is happening inside our classical computers that are built of the basic building blocks, transistors. And what is now the problem here? Well, the problem is that, and we have all heard, I hope, of, well, maybe not, but of Moore's law. Moore's law basically describes that we get more and more transistors on a chip. That means they become smaller and smaller. This is actually an older picture, right? This goes to 7 nanometer. Nowadays, we are already looking at transistors with typical length scales of 2 to 3 nanometers. Is that a problem? No, not yet. We can still do that. But at a certain moment, the scaling stops. At a certain moment, Moore's law will have to stop. Why do I say it has to stop? Because at a certain moment, you run into the problem that you approach the limits of an atom. And I wanted to visualize that a little bit by this little Lego picture here. So if you have a transistor and you build it of lots of atoms, just like this bird here, the top bird, you can still recognize it as a bird. If you make it smaller and smaller, the atoms, or in this metaphor, the Lego blocks, they don't become smaller. I mean, a Lego block is a Lego block. So you can make smaller and smaller birds, but at a certain moment, it's not recognized as a bird anymore. It doesn't work as a bird anymore. For the transistor, that means the transistor doesn't work anymore. So once we start approaching the scale of the atom, there will be a problem with Moore's law, with this continued scaling. So this all said together here, this is actually a little bit of an introduction into, okay, this is how our current computers work. And these are the problems that our current computers are facing. So if it becomes increasingly hard to continue with this silicon-based, with this electronics-based traditional computing, what should we do then to solve it? We need to solve this. We need more power. We need more efficiency. And I want to spend a few slides first sketching the problem, why we need it, or at least why we think we need it. And I give you here one example that is actually a little bit of an old example. I used this a few years ago. This is the amount of data that is being uploaded on YouTube, and the amount of data that is being downloaded from YouTube, and the amount of users. And I used this slide a few years ago, and yesterday I updated the numbers based on our current numbers, and they were vastly larger than a few years ago. Because what are we looking at? We are looking at simple movies. YouTube is just movies, right? We all of us basically know that, right? And of course, this is a funny movie, maybe of a dog. So there are lots of cats and dogs movies. There might also be documentaries. I'm not talking about the content. I'm talking about just the bits and bytes, right? And what we're doing on YouTube, over 1 billion hours are watched every day by 1 billion monthly users. And every hour, every minute, we upload 500 hours. So there's a massive amount of data going to the servers, from the servers, going through our networks. And all these movies are, of course, being processed, etc., in processors. So computers do this kind of work. So this is growing. And for us, it's very hard to grasp, actually, so why is this a problem? I mean, I didn't make the problem clear. I just said, okay, it's a lot, right? Now the problem becomes clear a little bit with this slide. As a heads up, I'm going to say, okay, it's a little bit controversial slide, but it sketches the problem. So there was this controversial statement a few years ago that a smartphone can use the same amount as a fridge. And okay, it's actually a little bit hard to calculate, but if you calculate it, and if you would, take a heavy smartphone users, you actually come close. So let's assume for the moment that's order of magnitude more or less the case. We are not aware of that, right? Because our smartphone, we plug in with a little battery, we plug in once a day, and it's hardly adding to our energy bill. Our fridge is adding to the energy bill. Fridges are huge. I mean, at the moment that in well-known stories in Brazil, when there's a football match in the break, everyone goes to the fridge, opens their fridge, they all start cooling, right? And then the power lines are out, the net is out. Fridges use a lot of energy. Our smartphone obviously doesn't do that. So why was there this, again, slightly controversial, but making the point, statement that a smartphone uses the same amount of energy as a fridge? Well, that's because the smartphone is just an interface. A lot of what's happening in the smartphone is, first of all, going through our network and then going to the data centers. I mean, YouTube movies are in a data center. Obviously, they are not on our smartphone unless you downloaded them. So it's just an interface, a gateway, a terminal towards these massive data centers where, and again, that's a little bit subject to how you calculate, but typically people say in the range of 3 to 10% of all our electrical power is consumed by the data centers and the networks, so by the internet. And this is vastly more energy consumption than the actual battery of your smartphone has to deliver. And this is, of course, going to grow, right? Because it grows because we get more maybe not more smartphones, but more devices like smartphones that will all make use of the internet. Those could be smart watches. Those could be smart glasses. Those could be other kinds. I mean, this is actually a very old-fashioned picture, right? That's a Star Trek tricorder. Things like that are actually starting to exist at the moment. I mean, I don't have a nice picture of that. It's mostly in the development stage of some new research, some new technology initiatives. But these things are starting to happen. So a lot of variables are already there or will be there. And on top of that, these variables are going to do more and more, right? I mean, we want to have all these glasses for virtual reality, for example. That means far more data going through. We want glasses maybe for augmented reality. So virtual reality, of course, you need a computer, you need a processor, and you go to this virtual space. But if you talk about augmented reality, we need to map the virtual space onto the real space. The coffee table here is obviously real. The couch is obviously real. What's on the couch, what's on the coffee table is projected on top of that, and you can see that through your glasses. There's, of course, a lot of computing power there. And even one step further, we can talk about perceptual computing, where actually you can interact with your digital images, with your digital environment. And that would require even more computing power. So we get more and more devices, and each of these devices is gonna probably require far more computing power and far more communication of the bits and bytes to be sent around. So the main problem that we are looking here, that we are facing, is exponential growth. I didn't put numbers with horizontal axis because that doesn't matter. Exponential growth is always the same curve. Flat, steeper and steeper and steeper over time until it becomes really, really steep. It is about the numbers though. What are we looking at? What is changing? I just put a few examples here. We have been talking about Moore's law computing power. Per decade, we get 30 times more computing power. Luckily, per decade, the computers become 60 times more energy efficient. And by the way, 30 times more computing power means per 10 years means 30 times 30 more computing power in 20 years. So that's getting close to a factor of thousands. The energy efficiency with which we send around data through the telecom networks, that's 10 times more energy efficient. Our mobile traffic per decade, that goes up by a factor of 80. And then we get all these additional devices, the Internet of Things. But also, do not forget, our cars also get connected. Connected with each other for assisted driving, for autonomous driving, but also connected with whatever happens around the highway, all kind of sensor systems there. So things basically blow up over time in technology. That's why we call these kind of things exponential technologies. Current technologies, current concepts in computing will not be able to pull this off for much longer. Of course, we know that technologies have always been changing. Actually, electronics technology, CMOS technology, silicon-based technology, it has been a replacement of tube-based technology, the old-fashioned computers that are basically the size of a whole room. So the transistor, the invention of the transistor by itself has been a huge revolution in that sense. I mean, we even had mechanical computers 150 years ago, right? So we know we get new technologies. So now the question, we need to look at other technologies as a solution for our future computers. And one of the things to look to, and of course I already gave a heads up in this in my title, is to look at things like light. And light is already proving that it could be very good for a lot of things. Our internet Our internet is basically enabled and made possible by light. It uses fiber optics, transparent cables in which you can couple laser light to basically connect 2 points for communication. And these optical fibers have been slowly replacing old-fashioned electrical wires, copper wires. In the past, we had copper wires. Well, if you take a copper wire, there's some kind of electrical signal going through the wire. And the point is that, okay, that works well. But if your amount of data goes up, so if we go to about 1 gigabit per second, which is a little bit the amount of data that a really high-end internet connection now gives you at your home, maybe. But if we look at those kind of connections, approximately half of your signal is lost after 10 meters. So most of your signal, you cannot transport your signal far further than tens of meters at these high bandwidths with copper wires. Fiber optics, though, work differently. So these are glass fibers, so transparent for light. So we couple in laser light, we modulate that so we get the bits, and that goes to the light through the fiber. And if we now increase the bandwidth, if we now have a high bandwidth of about 1 gigabit per second, we lose half of the signal, not after 10 meters, but after 10 kilometers, which means if you tolerate a little bit more loss, that you can have tens of kilometers, maybe even hundreds of kilometers of transmission, and you can still detect some signal. And that is 1,000 times more in length, what you get by replacing electronics, electrical connections with fiber optic based connections and light based communication. So this is about the length, the distance that you can bridge. There's another advantage of light. Light has the advantage that you can actually multiplex signals. So the fun part of light is that if you take light in one color, in this case schematically represented by red, in practice it's actually in the infrared, but okay, you cannot see that obviously. So schematically we say the red wavelength. Light in the red wavelengths, if I couple that into an optical fiber, together with light in yellow, green, and blue wavelengths, these signals do not interact. Well, depending on the material, but normally they do not interact. That means I can just bring them all in the same optical fiber, and techniques for doing that actually exist. And some of the techniques for doing that we actually all know, because maybe a lot of us have seen how a prism works, but I think all of us have seen that if you take a glass of water and you put it in the sunlight, that you can get these nice rainbowy patterns. So if you can take sunlight, white light, and you can sort of split it out into a rainbow, that means you can also do the opposite. You can come in with all your different colors of light and combine them basically with something like a prism into one beam of white light, and that beam goes into the fiber. Of course, you can do the same trick at the other side, and then you can demultiplex the different information streams. So light you can transport further than an electrical signal, but also you can multiplex all of these signals. And in a very simple example, if I put 25 gigabit per second on the red one, and I also do that for the yellow and the green and the blue one, I would have 100 gigabit per second overall bandwidth. With tricks like this, you can even achieve 100 terabit per second. And 100 terabit per second is basically 100,000 times more than the best internet modems or internet connections you get at home. So 100 times more than that. Obviously, you don't need that for your home connection, but that is, of course, needed in intercontinental transatlantic links, right? So, a little bit of history. This is not new, right? Optical fibers have been connecting us since the 80s. They connect our, I was just talking about transatlantic cables, trans-Pacific cables. fiber optics have been connecting us all over the world, our countries, our continents. This is still a slide from Denmark, so this is actually when my previous position in Denmark. So here you see Denmark connected, all the cities, data centers. But since the 90s, also to the home. Started in the 90s, but nowadays it's becoming really big, fiber to the home. But also computers. Well, mostly supercomputers and data centers. But fiber optics, optical connections are making an impact there. So this history. Now looking towards the future. So if fiber optics are connecting all of our cities, our data centers, our servers, maybe they're also gonna connect inside a computer, or maybe they're gonna connect on a server or on a motherboard, if you want to call it like that, connecting the chips, a processor, CPU with a graphical processor, a GPU, and maybe memory. That is already happening in lab scale, and very advanced servers, they might already see this. And then hypothesis further towards the future. Okay, if we are connecting processors and chips together, which we are already doing now in very high-end applications, will we also see that on a chip, on a processor, that there will be a little optical network connecting different parts of the chip? So that's the future, but the need is there, because people often forget that if you send a bit of information towards a data center, then within the data center, 10 to 100 times more bits are going around. And within those chips, maybe 1,000 to 10,000 more bits going around. So if you do something at, watching a movie at 100 megabit per second, then there are some processors maybe working at not 100 megabit per second, but 100 gigabit per second or more. So that's how things scale a little bit. But that's looking towards the future. Can photonics help out there? But if we want to do that, we need photonics that can actually go to this chip. And now I make a little bit of a jump towards the technology that is actually my personal research field, has been already for almost 20 years, which is photonic integration, or a little bit more popularly speaking, optical chips. So what's an optical chip? It is very comparable to an electronic integrated circuit. In an electronic integrated circuit, we have our building blocks, as I just said, like a transistor, but maybe also a capacitor, maybe also a resistor, and of course little copper wires to connect things. And we all put that on a piece of semiconductor, typically silicon. In photonic chips, optical chips, we do the same, but then for optics. So what you see around here are typical things that you normally can see in a lab, but I will just explain it so you know what I'm talking about, and then you will know what, you will immediately recognize the concepts. We have a laser, for example, to generate light, a photodetector to detect light, a modulator to modulate light, to switch it on and off, right? Filters to take one color and the other colors not. Here's your waveguides to guide light from point A to point B. And I already showed those gratings and prisms to separate light with multiple frequencies, multiple wavelengths into to separate those or to combine them. And what do we do in photonic integration? We take all of these components that you normally can find separately, and we bring them all together on a single piece of semiconductor. Just like an electronic integrated circuit, we're talking about stuff that is typically a few millimeters square to, let's say, a centimeter square. So very small. And of course, that enables us to take large optical systems and reduce them in size. This is a very nice, a little bit of a, let's say, marketing example from a Dutch company. They make fiber optic sensor readouts. And what used to be in a big box that is typically tens of centimeters by tens of centimeters, through photonic integration, they were able to reduce their whole system into this little device. And where these kind of devices, these kinds of readout units are typically on the order of tens of thousands of euros, this one could be on the order of hundreds of euros, or even cheaper. So a little bit more in detail about the advantages about photonic integration. Why do you want to do it? Well, what I was showing in the previous one, decrease size, weight, and power consumption. So make smaller systems. And if you make smaller systems, that means you can put them in places where in the past you could not put those things. Drones, spacecraft, aircraft, satellites, but also in wearable and handheld devices. I mean, we all have mobile phones nowadays, right? A lot of functionality could be put in there and is already being put in there. But also increased performance, right? I mean, things become far more stable, far faster, far more sensitive if you actually put it on a chip. And eventually decreased cost. And there are two important things on the decreased cost. First of all, that it becomes cheaper, that you can get it more easily. But also, of course, that you can get it in far higher volumes. If we talk about sensors, if sensors become cheaper, that typically means that it allows us to sense a lot of more information, to implement them ubiquitously, right? So we get far more information. Obviously, a little side note, chips, the first chip is never cheap, right? The first chip might actually cost you millions of euros. However, the last chip that you make might cost you only €1 or even 10 euro cents or something. So that is the scaling that is, of course, required. So this kind of technology is typically used for the higher volume applications. And just another way to highlight a little bit, I like this picture here on the right-hand side. This is old work from 2006 by a company, Infinera, who has been leading the way in photonic integration. So about 15 years old, right? And what they were able to do is on this particular chip to integrate, this is for communications, 10 lasers, 10 modulators, 10 wavelength lockers, basically control systems. And all of these components that normally you have to buy separately, and they all have to be packaged separately, and that adds to additional losses, inefficiency, cost. They were able to put everything on one single photonic integrated circuit, in one single package. And the reason I like this, not because it's state of the art, but I like this because 15 years old. And a lot of people think optical chips, actually a lot of people have not heard of it, but it's already powering and enabling our networks for at least 1.5 decades. It's an existing technology. We are now doing far more with it, but it's an existing technology that has been around for quite some while. And the next slide is actually highlighting that even more. What I do in this slide, I actually show the complexity of photonic integration, and I express that by the number of components per chip. That kind of metrics we know from Moore's law, right? Because in Moore's law, we look at the number of transistors, in this case here, starting with 1, so that's basically the invention of the transistor, right? And then slowly increasing the number in the blue dots here, increasing the number of transistors on a chip, typically with a factor of 2 every 2 years. So leading to, in the 1970s, 75 or something, tens of thousands of transistors per chip. If we do a similar exercise for photonics, although now starting basically 40 years later, when we started with photonic integration, as compared to electronic integration, and we plot in the red dots state-of-the-art chips with photonic integration, we can also see that that goes with a similar amount, a factor of 2 every 2 years, also to nowadays tens of thousands integrated components per photonic integrated circuit. So these trends are exactly the same, actually. Of course, there's an offset of 40 years, right? This ends at 1975, this is 2015. So obviously electronic integration is far older, far more mature. Interesting though, it's nice to stop at 1975, 1976, because you can, of course, argue, okay, 10,000 components per chip. Is that a lot? Is that not a lot? I mean, now we have 1 billion, right? So that sounds not so very impressive. Well, I just give you some food for thought here. In this time, Microsoft was founded and Apple was founded. So Microsoft and Apple were founded when the electronic technology had the same complexity as photonic integration technology. Well, I leave it for you to decide whether that the technology has potential to jump in on that sense, but it's a nice fact to put here. A little bit more in detail when we talk about photonic integration. So I want to, of course, add a little bit of technical details here. When we talk about photonic integration, what does it look in practice? Well, we have a wafer. So we make things with the techniques as we make transistors. So we have a wafer. And on a wafer, we then etch these little ridges. And these ridges are basically little optical fibers. They guide light. So here you see this whitish blob. And by etching this ridge, through this ridge, and we can make that long, short, we can make it in a turn, in a corner, etc. We guide the light. But this material is semiconductor material, so we can also do something with the material. We can, for example, put a little current through the material or put a little voltage over the material by building in diodes. We know that from electronics. I mean, it's semiconductor material. We can also do it here. The fun part is that if we put a little electrical signal on such a waveguide, we can actually delay it a little bit, or we can advance it a little bit. And that means we can control the phase of the light. And even more interesting is that if we, schematically represented by this red layer, if we add an additional layer, in technical terms, that's material with a slightly lower band gap. So that's material that would normally absorb light, which is great because if the light gets absorbed, we might use it for photo detection. I come back to that. But this particular material, which is actually the basis of our laser diode, so it's not so new, right? If we would inject current, we can basically add energy to this material and we can generate light. And we can also amplify light. So these are optical amplifiers. So there we can change the amplitude of the light. The fun part is now that if we do not add a current, but if we change the polarity of the electrical signal, that means instead of injecting carriers, injecting an electrical signal, we are sort of extracting an electrical signal if light gets absorbed. And that is what we call photo detection. The bottom line is that on a wafer, we can now make all these components, waveguides, and modulators for the phase of the light, and modulators for the amplitude of light, and even components to control the polarization of light. And in a similar way to electronics, where we were talking about a transistor, a resistor, capacitor, in a similar way, we now have a set of building blocks. And with this set of building blocks, if you consider them like little Lego blocks, you can then make circuits. I don't want to go too much into the technical details, but we can make circuits for additional functionality. I mean, I already showed you an example of a circuit that can do high bandwidth communication by taking multiple lasers and multiple modulators and bringing all these different data streams together. I already showed you an example of sensors, where we can, on a chip sense the signal that comes back from a fiber, for example, for structural sensing, and miniaturize all that. But we can also use it for LiDAR applications. We can use it for biomedical sensors. I will get back to that to show you a little bit of the applications. But the bottom line here is that we have these building blocks. They're like Lego blocks, and we can now nicely put them together in different sequences Just like that a transistor is obviously not a computer, but if we lay them out in a certain way, okay, then the computing can start. So just to give a little bit of a visual here, when we talk about photonic integration on a chip, we talk integration on a wafer. So chips are made on wafers in the electronics world and in silicon. And you can also, from silicon, you can make photonic integrated circuits. We typically talk about wafer sizes that have a diameter of about 20 to 30 centimeters. In other materials, this is material of indium phosphide, which is also a semiconductor. Then is maybe slightly smaller, maybe 10 centimeter in diameter. But that can still hold a lot of different circuits. So here you see all kind of different circuits. And here you see a close-up of one circuit. And what you see here is a design where all these different building blocks are put into a certain sequence. You can see waveguides here in a little bit of the darkish brownish color. It's not so well visible, but that's because they're very small. And on top, you mostly see these golden colored contacts. Those are typically electrical contacts to control the electrical, the modulators, the optical amplifier structure, the phase modulating structure, the photodetecting structures. So those are the leads towards the interface with electronics. So a die here can have many circuits. In this case, they're relatively large, so not so many circuits. And on a wafer, there can be many dies eventually. And this shows you how this larger volume is being reached. Now, the next slide is just to show off a little bit a slightly more close-up view, where you see all kinds of different photonic integrated circuits with different purposes. It could be for communications purposes, for wireless communication, for fiber optic communication. It could be for biomedical applications. But here you have a little bit of an idea of what it would look like on a chip. Combining different, let's say, laser elements here where you can see a contact, combining here an on-chip grating to separate those wavelengths, those colors from each other, etc. So historically, telecom, datacom, that is why we have this. I mean, that is historically why we get photonic integration. But we are looking to far more applications for the moment. I was already mentioning fiber optic sensors. You can put a fiber into a bridge, and then you can read it out, the optical signal that is reflected, and you can monitor the bridge, right? You can see whether it ages, whether you get little cracks. So you know when to do your upkeep because you have online monitoring. You can even measure that cars are passing by. You can even measure where the cars are on the bridge. Many other applications, biochemical sensing, Ebola sensors, you know, so you had Ebola sensors when there was a pandemic for that. Now we have a corona pandemic. Now we have corona sensors, also on photonics based. Wireless communication, quantum technology, microwave technology, LiDAR already mentioned. And I come back to the point, can photonic integration also play a role and push something in the field of computing? And the first thing I'm going to discuss here is, okay, can it maybe assist electronics? I have spent a lot of time explaining, okay, photonics is very good for transport of information, for communication. We need communication. We need communication on a chip. This is a quite old picture, 15 years old, by IBM, where they had the vision that their future processors, they would be in one layer, there would be a memory layer on top of it, and on top of that, there would be a photonic layer on chip to connect all of this, to basically solve the interconnect, the communication bottlenecks on a processor chip. And over the last 1.5 decades, the community, not only IBM, but the community has been working to actually realize lasers, modulators, photodetectors in photonic integrated circuit technology. But not only that, actually there have been thousands of lasers, thousands of modulators. But the very interesting part is that we were also able to do that in a way that it is compatible with the silicon electronics technology. So life is not only about making a new technology, but it's also about interaction, right? So in silicon technology, or at least in technologies compatible with silicon, we are now able to make all of these components. And that would basically allow you to have this photonic network on a chip. And more than a decade later, actually a lot of this became a reality. So this is work, it's a little bit of a technical picture, but it doesn't matter. This is work by MIT. It is actually meant to sort of impress you because you cannot see a lot on this picture. That's because it's a picture of a chip that contains over 70 million transistors, and at the same time, over 800 photonic components, all made in the same CMOS compatible technology, in the semiconductor compatible technology. And this is a processor that has computational power, that has memory, and photonics for communication. And what this thing exactly does is it allows now, this is a little bit of a schematic, where they take one of the chips here, they use that as a processor, they take another chip physically as a different position, and now they connect it with an optical fiber. And they can do that because they have the optical transmitters and receivers on the chip. So they don't need anymore those metal pins that you have underneath your normal processor. Well, of course, you still need that for power, but not for communication. So they still have externally a laser. So laser light shines into the memory chip. If you want to download some information from that memory chip, then the laser light is modulated. So the bits and the bytes are put on the laser light, ones and zeros, right? Whatever data you want to get out of here. So then the modulated laser light goes to the processor chip, where it falls on a photodiode, which is placed on the chip. And then the transistors on the chip, which are right next to the photodiode, they read that and they can process it. So this is now the first monolithic, so on one chip, implementation of a combination of electronics and photonics, basically allowing you to replace electronic communication in the chip-to-chip communication. You can even bring that further. So I just only have, this is chip-to-chip communication. Myself, I've been working also to say, okay, can we also speed up memory? So nowadays there are even magnetic memory on a chip. And some of these memories, some of these magnetic memories, you can actually change by optical illumination. And you can sort of see why is a magnet, why is that memory? Well, because magnetization can go from north to south or from south to north. So you have two states. Two states is binary. Binary means a bit, and a bit you can store in the magnetization direction of the memory. And if you now think about illuminating that optically, addressing all these memory bits with optical pulses through a photonic network on a chip, then you can make very fast and energy efficient memory. But this is still in a very early stage, whereas the technology I just showed you is actually being commercialized now by an American company. So what we have been looking now at is basically, how can photonics assist electronics in making better and more efficient computing? Another way how photonic integration can push the field of computing is by actually trying to replace electronics by looking at completely different computing paradigms. And I also want to show a few examples of that, actually. And I want to show you basically three examples, starting with the oldest one, which has been around for a few decades, I think, optical computing. Optical computing is a very interesting concept. I give you a very, maybe a simplified example. Optics is very good with images. I mean, an image is basically optics, right? Without optics, without light, there is no image. So let's say you have an image and you have a bunch of lenses. You can, of course, project that image. We all know that. Actually, we might know that less nowadays, because in the past we used to have slide projectors, overhead projectors, where you could actually see the lenses. So you could go from a small slide to a screen, or vice versa. Cameras work like this, where of course a real life image is projected on nowadays a CMOS display camera array, CMOS chip. In the past on a film. So we all know images and light go together hand in hand, right? And with lenses we can manipulate that. The interesting part of this setup, which is textbook example, and maybe depending on which country you're from, a lot of you have actually having had to calculate these kind of things in high school even. The interesting part is, here's an image plane. Here's another image plane, but what happens between the lenses is a little bit different. Between the lenses, if I go from top to down, here I look at the real space. I basically see the top of the head of the lady, then the nose, then the mouth, and then going down. In this plane, I see something different. In this plane, I see mostly, technically speaking, it's the Fourier plane. So it's basically the Fourier transform, but qualitatively speaking, it's basically a plane where I see variations in the image, slow variations or fast variations. And if I apply filters here, I can basically filter out the fast variations or the slow variations. So if I filter out the slow variations, then that basically means I filter out that this goes from white to dark to white. But I will see the fast variation, so I will be able to detect the edges. So that is what you see here. If I only see what we say the high frequency components, I basically see edge detection. If I just do the opposite and I kick out those edges, I see a blurred image. Well, if we just look at image processing, we all know that if we would do this on a computer, it will take actually some time. Nowadays a little bit less, but in the past it would take a lot of time because we are doing it with those transistors. But optics gives it to you for free by just adding a filter. And it does it in a massively parallel way, and it does it with speed of light. Because all these pixels, if this would be a simple display, let's say 1000 by 1000 pixels, that is 1 million pixels. They go from here to here with speed of light. This could be a CMOS display, again, 1000 by 1000 pixels. And if I would vary this with, I don't know, 50 hertz, then I would basically process 1 million times 50, all immediately as we see it, on the fly. Of course, this is for images. And you can argue, okay, that is not so interesting. But if we are able to encode information like in an image, and for example, we can do that with things that are maybe more appealing than image processing, like genome sequencing, weather forecasting, radar signal processing, aerodynamic calculations. It turns out that these classical optical computers can actually have a lot of added value there. And so much that actually some companies, they are actually bringing this to the market. And there's a British company that actually brings it to the market. And now I come back to the photonic integration, that takes these concepts and tries to bring it to the market based on a photonic integrated circuit. So old concepts where we make use of the massive parallelism of optics, that we can do a lot of things at the same time, and that we can do it very fast. And the British company Optical is now putting all of this on a photonic integrated circuit. How they do it exactly, that's too much detail for here. And of course, they don't disclose that anyway. But photonic integration, optical chips are bringing classical optical computing to the market now. And they bring that to the market as what they call an optical accelerator for Fourier transforms. So it's not like a generic purpose processor, but for specific purposes. And that's not a novel concept because we already have that, right? We have a GPU, a graphical processing unit, next to a CPU. So it's not so novel. It's a not so novel concept in that sense. And it basically means that some of the calculations you route to this chip and some other calculations you route to your normal CPU. So this is classical optical computing. Nowadays, a lot of people talk about deep learning, artificial intelligence, and neural networks. That's actually a different way of computing, and that's actually a way of computing that is modeled to how our brain works. And this is one particular implementation. I want to go to the schematic with you a little bit of an artificial neural network. And very schematically, what is an artificial neural network? That is where we have an input layer, so different inputs. I show 3 here. They go to a first layer where something is happening. All these signals are combined in all of these points. What we call neurons. Signals are brought together. Neurons, then depending on all the different signals that come in, this neuron does something. It gives another signal and is combined with all the other ones. And then it gives you an output. And that is very abstract. So let me make it a little bit more concrete. This could be a picture, the input layer. These could be pixels of a picture. And the role of a first layer could be to detect shape. The second layer could maybe detect texture. And then we can achieve something that we can call image recognition. To make it even more concrete, we can actually give a picture. So a tennis ball, right? So the first layer looks at the shape, right? And the shape is round with an S in it, this thing here. And the second might look at texture, and it might recognize it as green and fuzzy. And then we can easily say, okay, the outcome is a tennis ball. Of course, it needs to know, first of all, that it is a tennis ball. So you first need to train it. So you have to offer this picture and then say, hey, it's a tennis ball. So every future time you see something that is round with an S shape and green and fuzzy, then you always conclude it's a tennis ball, right? That's how, in some ways, artificial intelligence works. You offer these pictures and then you train it. But then also, of course, the same network, if you apply it to a camera on Wimbledon, for example, it will always be able to detect the tennis ball and separate that from the players. This kind of approach, where all these neurons, where all these signals are being brought together, that is now also being brought together on a photonic integrated circuit. What you can see here, well, it's so dense that you can hardly see it, but there's some color overlay. Different signals are being offered. These signals on the photonic integrated circuit are being combined with each other. And eventually they are then fed to one of these neurons where they either trigger something or not. That depends actually on what you want to do with it. That is reconfigurable. And doing it like this, and that's the claim of this was work by MIT, published here in Nature. The claim is then you can be far faster, far more energy efficient than our current processors. And companies like Lightelligence and Light Matter are startups that came actually from this work. So also DIT is going to the market. So photonics-based neural networks, they go to the market as we speak. And then a final computing implementation. And I don't want to go too much in detail because that's a topic by itself, quantum computing. Quantum computing is not normal computing. At the beginning of the talk, I introduced the fact that normal computing is binary. We have ones and zeros, and we switch those. And we were talking about Moore's law. Moore's law is basically saying, okay, we grow the number of transistors per chip. And as a result of that, we grow the computing power per chip. And that goes basically 1 in 1. Well, quantum computing is different. In quantum computing, we're not talking about a 1 and a 0. We're also not talking, as was in the neuromorphic computing, where we basically have an analog signal. So in an analog signal, it's a 1, 2 up to a 0, or a 0 up to a 1. But in quantum computing, it's a 1 and a 0 at the same time. Without going into detail, that basically means that we don't have this linear scaling anymore. We now get an exponential scaling. So whereas Moore's law says twice the amount of transistors, twice the amount of computing power, quantum computing says twice the amount of transistors, twice the amount of that they call qubits. That's the equivalent sort of you know, the bit, huh? Twice the amount of qubits, 4 times or maybe more times the amount of computing power. So the scaling is far faster. However, quantum computers, I mean, conceptually they exist, but competitively they don't exist. Idea is beautiful, reality is a little bit different. So there are still problems with errors in quantum computers. You need to cool them. And of course, quantum computers will also not be general purpose. Just like the optical computer, a quantum computer will basically be a coprocessor, likely in the future. Nevertheless, some problems are big enough that you would be really happy to have one, like encryption, but also like drug medicine development. So 2 small examples where photonics plays a role here. Qubits, the building blocks of quantum computers, can, for example, be an ion, and normally an atom or an ion. And where photonics can play a role, that normally you see these in physics labs with all kinds of lasers around it. And this is work by MIT, where they try to, okay, let's try to shrink that to a chip level. Let's take that whole optical lab and put it on a chip. And chips, as we know them, as I already told you, they combine electronics and photonics. So in this particular case, the electronics is being used with an electromagnetic signal to actually trap the ion, to let it hover above the chip. And then with the photonics, you can then excite and read out and manipulate with all kinds of colors of light this ion, this qubit. And you can have the photonics emerging with these little couplers out of the chip. So you can combine an electronic trap, like an electromagnetic trap, with the photonics. All, as you can see here, on a 1 by 1 centimeter chip scale. So that's an ion qubit. But you can also do that with photonics, right? Because photons are also have quantum properties. So you can also use the photon as a qubit. And what is happening here, and this is a very complex looking chip, but this is a chip, just a photonic integrated circuit with technologies as we know it. Laser light is coupled in, and in these little spirals here, the laser light interacts with the material, and spontaneously a single photon at a slightly different color forms, or maybe 2 photons. And these single photons can then be used in this network to actually do computing, quantum computing. So this is work by Bristol University in the UK and DTU in Denmark, where they actually made these chips. An interesting part here is, by the way, that these chips, they work at room temperature. They don't need cryogenic cooling. So these were some examples of quantum technology. So let me wrap up, actually. We have been talking about exponential growth. There are many ways to emphasize what is exponential growth. We do have exponential growth. I mean, the amount of connected devices, the amount of communication, the bandwidth, the data we send around the world, the computing power we have and need. The interesting part of exponential growth is if you would be on an exponential curve, if you would stand there, if you look back in history towards the past, the curve always looks flat, like a flat land. However, if you look forward, the curve always looks very steep, like the Himalayas. The interesting part is that that is at every place of the curve. So if you go forward, I mean, we are facing huge technological challenges. But basically, those challenges were there last year, and they were there 2 years ago, and they were there 10 years ago, and actually they were there 100 years ago. Of course, if we climb the mountains of the Himalayas, after that, you will find mountains that are maybe 100 kilometers tall. So it continues and it continues. Exponential growth is really hard to grasp. As a final slide, well, a final slide with content before I wrap this up, maybe some food for thought. This is a very famous slide by Ray Kurzweil. Kurzweil is nowadays a futurologist at Google, and he basically mapped computing power over time. And computing power over time is growing exponentially. And here are all the dots of doing that. And what we have just been discussing is how can we keep computing power on this track? How can we make sure with future technologies that this track will continue? And now he's extrapolating. So now he's just drawing a line. Okay, let's assume you scientists and industry will keep on doing what you're doing. Where do we end up? So he's basically extrapolating this line towards the future. So from this point on. And then he's comparing it with some benchmarks. So we are already at a stage that artificial intelligence, computing power exceeds an insect brain. We are around a mouse brain or slowly exceeding that. And we are getting close to exceeding the brain of a human being. And that's an interesting point, right? And that's the point what he calls the singularity. So the point where artificial intelligence crosses human intelligence. Why is it called the singularity? Because up to that point, we can still imagine what it means. Because we know what an insect does, we know what a mouse does, and we even know what our fellow human beings do. But we do not know what someone beyond a human being does. I mean, okay, a little bit, that's an Einstein, right? So we have a one step further is Einstein, but beyond Einstein, we don't know. That's why it's called the singularity. And the singularity is, I mean, this is a little bit vague when it will happen, but, you know, 10, 20, 30 years, those kind of time frames, those are the interesting time scales here. And what that means, yeah, that is a little bit of a philosophical thought for, to end this talk. One final slide. Actually, the interesting part is, this is the first presentation ever given on behalf of, or with the frame of the Eindhoven Hendrik Casimir Institute, which is an initiative of the TU Eindhoven, my university, where we bring together photonic technologies and quantum technologies to do exactly as what I've been laying out today, working on the future of computing, working on the future of communication, and working on the future of ubiquitous sensing, all enabled by these integrated technologies. And of course, eventually to make our society, our information society, better, but also more sustainable, because energy efficiency is obviously key here. With this slide, I would like to thank you all and give the word to Martin in case there are some questions.